Hello everybody. In this video we're going to be covering one of the sections from chapter 9, Electrons and Atoms and the Periodic Table. In this section we're going to be talking about the Bohr model. So the nuclear model of an atom that we've been using so far, it doesn't explain how the atom can gain or lose energy. A very smart man by the name of Niels Bohr developed a model of the atom to explain how the structure of the atom changes when it undergoes energy transitions. And this led to a really big idea, okay? And what it was that the idea was that the energy of an atom is quantized. That means that the amount of energy in the atom was related to the electron's position in the atom, and that the atom can only have very specific amounts of energy, and it can't have any of the energy states in between those. And this is kind of a weird idea that's hard for people to wrap their minds around at first, because it's just not true in the macroscopic world that we live in, right? Things can have any energy state they want. For instance, a ball can be any distance. If you're bouncing a ball, you can be any distance between your hand and the floor. But in a quantized system, it can only be discrete distances between your hand and the floor. In the Bohr model, electrons travel in orbits around the nucleus, much like the planets. They're more like shells, though, because they are three-dimensional, right? They're like a sphere around the nucleus rather than a path that it follows, like a circle. The farther the electron is from the nucleus, the more energy it has. Okay, so here's the nucleus, and then here are the various orbits that it can have. Each of the orbits has a specific amount of energy, and the difference between them is not always the same. Okay, so just like we gain potential energy climbing up a ladder, the idea here is that instead of having the same energy with each rung, we actually have different amounts of energy that we're gaining each time. The energy of each orbit is characterized by an integer. The larger the integer, the more energy an electron in that orbit has. Okay, so N1, N2, N3, N4, N5, N6, and 6 is the most energetic. And that's because it's farther away from the nucleus. This integer, n, is called the quantum number. When the atom gains energy, the electron leaps from a lower energy orbit to one that is further from the nucleus. All right, so energy comes in, and the electron jumps up to a higher orbit. However, during that quantum leap, it doesn't travel through space between the orbits. It just disappears from the lower orbit and appears in the higher orbit. And that is a result of that quantization. It can't be in between orbits. It can only be in one orbit or another. When the electron leaps from a higher energy orbit to one that is closer to the nucleus, energy is emitted from the atom as a photon of light. This is a quantum of energy. We can picture that here. So if this is a hydrogen atom, it's got its nucleus, it's got an electron here at n equals 1. Energy comes in, that could be in the form of light, and then it jumps up to a higher energy n equals 3 orbit. All right. After that, it will relax down back towards the n equals 1, and during that time, it's going to emit a photon of light. The wavelength of that photon is going to correspond to the energy difference between n equals 3 and n equals 2 in this case. The Bohr model of hydrogen, the lowest amount of energy hydrogen's one electron can have, corresponds to n being 1 in the n equals 1 orbit. This is called its ground state. When the atoms gain energy, the electron leaps to a higher energy orbit, and this is called its excited state. But the reason that it can't stay in that excited state is because the atom is less stable in that excited state. So it will always release extra energy to return to the ground state. This could be either all at once or in several steps. So if we went and thought back to the picture that we just saw, it could have relaxed all the way back to n equals 1, or it could relax down to n equals 2, emit a photon, and then go from 2 to 1 and emit a second photon. Every hydrogen atom has identical orbits. Okay, so different hydrogen atoms aren't going to have different orbits. They're going to have the same one. So every hydrogen atom can undergo the same energy transitions. But again, because the distance between those orbits in the atom are not all the same, no two leaps in an atom will have the same energy. The closer the orbits are in energy, the lower the energy of the photon emitted. The lower energy photon is going to have a longer wavelength. This is how we get the emission spectrum that we saw before. So here we can see a picture of that, right? When the excited, when we have an excited state, so it got excited up, okay? If it transitions from n equals 3 to n equals 2, then we're going to see a emission of a low energy photon, and it's going to have a longer wavelength, so it's going to be red. When we have it going from n equals 4 to n equals 2, we had a larger transition, so we're going to have more energetic light emitted, and that's where we get this blue-green line here. And when it goes from n equals 5 to n equals 2, it has an even longer distance to relax. Then we're going to see the emission of the highest energy light, in this case of violet. All of the spectrum that we see in the visible light has to do with it transitioning back down to n equals 2. There's a whole other series like this where it transitions back down to n equals 1, where we're actually emitting ultraviolet light. And there's another one where it transitions down to n equals 3, where it's emitting infrared light. The mathematics of the Bohr model very accurately predicts the spectrum of hydrogen. There's something called the Rydberg equation that we can use to predict this. But it starts to fail when it's applied to multi-electron atoms. Okay, and the reason for that is that the only reason that we can do it for hydrogen is because there's only one electron. Once we have electron-electron interactions, we can't use the same math that Bohr did and get reliable predictions. And so we needed a better theory, and that's where quantum mechanics come in. We're not going to cover quantum mechanics in this class, but I just wanted to give you guys a little bit of an idea here. It really all started with a guy by the name of Erwin Schrödinger, and he applied the mathematics of probability and the ideas of quantization energy to some physics equations. Specifically, he was looking at Newton's heat exchange equations, and that were capable of describing waves. And he came up with something called the Schrödinger equation. And this equation, it allows us to get reasonable predictions by using probability. So we can now talk about the probability of finding an electron with a particular amount of energy at any particular location in the atom. So rather than knowing things with certainty, we can now have this probabilistic model, which has really allowed us to do a lot in this field, and is leading to new breakthroughs like things like quantum computing and stuff.